Bunnies love one another. A lot. If you put a pair of rabbits in a vast field covered in fresh grass, they will reproduce like mad. The number of fluffy pairs grows according to the Fibonacci sequence. To write a function giving the terms of the Fibonacci sequence, you will need recursion. To make this function efficient, we will use memoization. Let's get ready to count bunnies. The first few terms of the Fibonacci sequence are 1, 1, 2, 3, 5, 8, 13, 21. Here is how this sequence is constructed. The first two terms are ones. Thereafter, each term is the sum of the previous two terms. 1 plus 1 is 2, the third term. 1 plus 2 equals 3, the fourth term. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. And 8 plus 13 is 21. This process continues forever. Our goal is to write a function returning the nth term of the Fibonacci sequence. Our function should be fast, clearly written, and rock solid. You may think this will be simple, but by the time we are done with our function, it will be more complex than you may expect. By the way, some people argue that the sequence should start with 0 and 1. If you encounter this situation, don't panic. Other than the 0, the two sequences are identical. People love to debate the smallest of details. Let's now write the function. We begin by giving our function a name. We will follow the Python style guide and use all lowercase letters for the name of our function. There is a single input, n. This function will return the nth term. To begin, we handle the starting cases. If n equals 1, we return the first term, 1. If n equals 2, we return the second term, 1. If n is larger than 2, we return the sum of the previous two terms. Because this function is calling itself, we call it a recursive function. Let's test this function to see if it works. We will print the first 10 terms. Notice that our range is from 1 to 11, not 1 to 10. That is because the range function does not include the final number. Frustrating, I know. Now, run. Our function worked. Does this mean we are done? Before we move on, let's test our function for a few more values. What if we display the first 100 terms of the Fibonacci sequence? Run. Well, this is disappointing. Our function is slowing down. It's virtually useless beyond a few dozen terms. Why is this? And how can we fix this? To see why this function is so slow, look what happens when it computes the fifth term of the sequence. Because this is a recursive function, Fibonacci 5 returns Fibonacci 4 plus Fibonacci 3. But Fibonacci 4 returns Fibonacci 3 plus Fibonacci 2, and Fibonacci 3 equals Fibonacci 2 plus Fibonacci 1. But now the function must make another recursive call because Fibonacci 3 equals Fibonacci 2 plus Fibonacci 1. Our poor computer is repeating itself needlessly. Since Fibonacci 1 and Fibonacci 2 are both 1, we finally get the answer, 5. Our simple recursive function is careless. We are making it repeat itself over and over and over and over. There is a simple cure to this madness: memoization. The idea behind memoization is simple. Store the values for recent function calls so future calls do not have to repeat the work. There are several ways to do this in Python. We will first implement memoization explicitly so you can see how it works. Then we will use a built-in Python tool that makes memoization trivial. To begin, create a dictionary called Fibonacci Cache, which will store recent function calls. Next, let's rewrite the Fibonacci function to make use of cached values. The first thing we will do is check to see if the value for the nth term is in our cache. If it is, then simply return it. Otherwise, we must compute the nth term. But we will handle this differently than before. We do not want to simply return the value. Instead, we will first compute the value, cache it, then return it. We compute the nth term the same as before. The first and second terms are both 1. Otherwise, we make a recursive call to compute the nth term. Finally, store the return value in our Fibonacci cache dictionary, then return it. Let's see if this function performs better than our first attempt. Much better. Let's really put this function to the test and display the first 1,000 terms. Impressive. Now that you have seen an explicit implementation of memoization, I would like to show you a simpler approach. For this, let's return to our first version of the function. This function is appealing. It is clean and simple. From the FuncTools module, import a decorator called LRU cache. This stands for least recently used cache, and it provides a one-line way to add memoization to your functions. To use this, write @LRU cache before our function. In parentheses, enter the number of values to cache. By default, Python will cache the 128 most recently used values, so if you do not specify a max size, you will still see benefits. Our original function will now operate very quickly. As proof, let's print the first 500 values. Much better. A simple function with fast performance. But our work is not done. What if we call the function and pass in the value 2.1? Or -1? Or the string 1? In all cases, the function did not know what to do. That is because we did not first check that the argument was a positive integer. Let's fix this. First, check that the input is an integer. If it is of the wrong type, then raise a type error telling the user what argument is expected. Next, verify that the argument is a positive integer. If not, raise a value error with the same message. Now, if we call our Fibonacci sequence with a float, non-positive integer, or any other forbidden value, the user will receive a helpful error message. By the way, there are many ways this method can be shortened, but we have opted for clarity over compactness. Short and clever code can be fun to write, but it often torments others. Let's take a final look at the first 50 Fibonacci numbers. As you can see, the numbers grow quickly in size. But how quickly? To see, we will compute the ratio between consecutive terms. Interesting. The ratio between consecutive terms in the Fibonacci sequence appears to converge to a number. In fact, the ratios converge to the golden ratio. You can learn more about this in our video on the Fibonacci sequence and the golden ratio. Like rabbits, recursive functions can quickly take over. Caution must be exercised. Otherwise, like Fibonacci, you will end up with a fuzzy-wuzzy mess on your hands.